thresholding thing, and yeah. So this is like all about the activation functions that we have for offering our neural network a non-linear angle. And this is like everything that you need to know about neural network. And I think like with this principle, everything else can be like designed with some more detail. So you need to know about a lot. So this is one way of updating the weights. So this is the one way of auditing the weights. And if you so there are 4 or 5 more ways to like update this weight faster. And there are 4 or 5 more ways to find the error as well. So here in the error term, I just subtracted from the final values, but there are methods such as mean square error, negative log likelihood, and binary cross entropy and cross entropy. So these are the 4 types of error that I will discuss when we will code, and when I'll exactly show you how do you like how do you use this functionality in PyTorch, and sort of and which laws you need to use for which problem in hand. So this is like this is like talking about everything that you need to know about neural network. And I think I will stop here for a short break. uh, so how to apply activation function on the linear function? So you just apply on top of that. So uh, let's say you get z here, right? So this is the z that you are getting from this point. So this is a z that you are getting here by multiplying x xi with wi. And if you're getting this z and you need to apply sigmoid on top of it, what you will do is that, so y hat will be the value of the function of sigmoid is 1 by 1 plus e to the minus x. So it will be 1 by 1 plus e to the power minus z. If you want to wish to apply ReLU, it will be maximum of 0 and z. And if you pass values to x, and if you assume, so if you pass some values to x1, x2, x3 to up to xn, and if you assume some value of x1, w1, w2, w3, and w6, if you multiply x1 with w1, x2 with w2, x3 with w3, and so on, and you add them, and you add the bias, the z is nothing but a number. So if it is a number, you can easily find if z is greater than 0 or not. If it is greater than 0, it will be z. It will be that number. If it is less than 0, it will be 0. Similarly, you can find this function as well. Like if let's say if the value of z is 2, or let's say the value of z is like 0, you can say 1 by 1 plus e to the power minus 0, which is 1 by 2. Value of y hat will be 1 by 2, like that. Has the activation function improves the performance of neural network? Yes. Why improves? Because uh, without activation functions, you cannot actually uh, do neural network prediction for non-linear tasks. Since most of the tasks that you see in the real world are non-linear, are not just linearly depend upon the factors that you are seeing. So you need to apply activation function to get good results. With just linear functions, you cannot represent the real world functions, which are very non-linear in nature. Yeah. So is there any questions that you want to ask? So if you want to ask any question, you can keep your questions and start asking them in the chat. I think we have we have been doing this for 2 hours, and we will take a short 10 minutes break or 15 minutes break, and we will meet exactly at it's 9 like 4:40 p.m. Indian time. So if you have questions, you just keep posting it in the chat.
Recording in progress. Recording in
How do we
progress.
know which activation function should we use, should be used out of the four? So there is now four actually. If you see, like, there are a lot of activation functions, but these four are the common ones which we use in our daily basis. And out of these, so as I said, sigmoid should be used in the end layer if it is a binary classification problem. But by binary classification, I meant that if the problem is asking you to decide whether the person will live or die, or like, if the this image is a cat or dog or something like that, like this is two between two. If it is, if it is a problem where you need to find the, like, sort of uh, predict the image as one of the 10 animals or 10 object, in that case, uh, it will be like, softmax, not sigmoid, because softmax distribute the probability score among uh, all the classes, and but sigmoid only distribute between two. And ScanH and ReLU. So for computer vision task, like for image classification and all, we generally use ReLU as an activation function in the network, but TANH is something that we use, like, we use TANH and ReLU interchangeably. You can use also sigmoid in the intermediate layer if you want, but for like for simplicity, I would say that it's again a hyperparameter. By hyperparameter, I would say that by hyperparameter, I would say that this is something you need to play around and find every time you do, every time you, like, perform a task. For some task it is already done, and people will say that, okay, for this task this activation function is good, but there is no single activation function good for, all the tasks. You have it is depending upon the task. And next question is, uh, there are a lot of advancement. Next question is from Dr. S. Chandramouli. There are a lot of advancement came in ANN. So how is this helpful? So if you look into what I mentioned earlier, so the advancement came in, like, some areas of the ANN, like if you see, the number of variables will increase, the number of layers will increase, the number of this number of neurons in each layer will increase, and also the way you update the weights, the way you like, initialize the weights, the way you calculate the loss will be different. So there are improvements in these areas. Like, I calculate the loss just by subtracting. Someone will come and say that, let's not just subtract, let's just take the square difference of it, which is the Euclidean distance. Someone will tell that, let's just find the entropy between these two, like, two variables, and see if we can minimize the entropy. So this is different way of calculating the same error. The more way you explore, so the advancement came in different ways, and for different tasks, different ways of, like, calculating the loss, also updating the weights like W1 to Wn, or the A that I started with, and also like the way you update, the amount you update. So there are a lot of improvements in these areas where you need to decide upon how much or how you to update. But the underlying task of, like, forward propagation, the underlying task of, like, randomly initializing first, then propagating it forward, finding the loss, and back propagating it will always stay the same. It will not change. So it is this four step will always be the same for any neural network that you see, even if today. So this is my answer to the question. And next question is, which activation function is better and why? I already told, it depends upon the task. So can we get the Google Colab link like yesterday for today's class? Yes, sure. If you send the code, you can copy the notebook and work along with you. Okay, sure. I'll share this and make it public. Anyone with the link can access. So I'll copy the link. Done. And I'll paste it in the chat. Yeah. And Yes. Okay. So I've shared this day 2 code. If someone cannot find it, let me know now. I'll start running this code and getting the results out of it. When one is not able to find the code, do let me know. Yeah, I hope everyone is able to access it. And I'll start by running this code along with this. Before that, uh,
Yeah. I hope you can hear me properly. And yeah. So before starting this, so Radha is saying error. Radha, you didn't run the first block, so I'll just show you now right now. So there is this flash block which says import torch. So yesterday we learned that how we can import things that is not native to Python, and we can always import something that is not native to Python, work with it. And torch is a sort of library that is developed keeping in mind the sole purpose of like using deep learning very hassle free. So I will now show in code that how that four step that I discussed, random initialization, then forward propagation, backward propagation, the loss calculation and backward propagation and word updation can be done in 4 lines. So I'll just show you right now. So first you need to import torch. So you have to do that. Up. Okay, so you need to do that. Then so torch is works on tensors. So I'll just discuss what a tensor is so that you can have a good understanding of what a tensor is. Yeah. If you talk about tensor is something so you see a one-dimensional number one, so it is one-dimensional. If you see something 2D, it's like 2, 3. It is two-dimensional. You also represent it as R. also it is R2 or R square, and this is also 2D, which is R square. But when you go two-dimensional, oh sorry, so this is all one-dimensional. So when you go two-dimensional, it is two-dimensional and it is represented R square. So what will happen if you go beyond two-dimensional? So what will happen if you have R3? So to represent R3, we have to build a little 3D sort of thing. This is one dimension, and there is another dimension. It's coming from here. You can say put 1, 3, 7, 9. So if you find itself, it is 1 cross 1. Itself, it's 1 cross 2. Itself is 1 cross 3. Itself is 2 cross 2. But if you find this set, it is 2 cross 2 cross 2. Like that. And if you have something like 3 of this, it's a 3D matrix. And its size is, its height is 2, width is 2, and the depth is 3. Better represent like this: 2 cross 2 cross 3. So so we call this as number. One second. So we call this as number. We call this as an array or a list. Same for this, same for this, so same for this, and we call this as a matrix, and we call this as a 3D matrix. So why is it necessary to but we can also say that this is a 1D tensor of shape 1 cross 1. This is also a this is also an 1D tensor of shape 1 cross 2. This is a 2D tensor of shape 2 cross 2, and this is a 3D tensor of shape 2 cross 2 cross 3. And if you can go 4-dimensional, we still can say that 4D tensor, or we can say 17D tensor, but we cannot visualize that as we visualize this up to 3D tensor. So we cannot visualize this one, but the matrix, the vector matrix, and if it goes further, if the number of dimension in a way, it will be it will belong to R17. It's similar to R2 and R3. So if a number is growing in dimension up beyond 3, we don't have a name. That's why we just put 1D, 2D, 3D, 4D tensors. So you might be asking like why this term tensor is necessary and why we should care about it. Because as I mentioned earlier, if you have some input x1 to x6, it is very common that people will represent this as a matrix X, which will contain x1 to x6. And once your neural network grows, it will not be just one layer. What will happen is that, let's say you have this input and you have this hidden layer where you have 4 neurons, and you will now connect all these things to all these things, and the output layer will be like this, because since you just connect the neurons, and so this will be like x1, x2, x3. The weight now will now will not be w1, it will w11, and it will be w12, and so on. So if you plot these things, it will be like x1 to xn, and w will be a matrix of w11, w12, w 14, w21 up to w24. Similarly, wn1 to wn4. And if you multiply this x into w, x size is 1 cross 4, w size is 4, x size is 1 cross n, and w size is n cross 4. Your result will be 1 cross 4, which will be this output here. And then you again take this 1 cross 4 and multiply with w21, w22, sorry, not w layer 2 to 1, layer 2 to 2, w layer 2 3, or you can just put 1 to 3, and w layer 2 4, which is again f4 cross 1, and you will get 1 as output, which is the same as the output layer. The thing that I'm trying to say is that once you grow in numbers, you will not sort of work with individual numbers or individual weights. You'll always be updating these weights in bunch, like updating the first block of weight or second block of weight. So updating the first block of weight or second block of weight, and you need to play around with the this matrix. Okay. So coming back to our discussion, we should be caring about the tensors and what is the uh, like dimension associated with it. So going to the next section. So how do we create? So sort of how do we create these tensors in PyTorch, and how do we represent the existing data as a tensor so that we can multiply? And so if you represent your data in the PyTorch tensor, what it will do is that it will leverage the GPUs, the graphic processing unit, to parallelly calculate and parallelly update these weights, so that all your weight updation can be done in just one go. So let's just jump into the code. Let's just try to import the torch and try to find you know try to find how to get this tensor. So if you run the first block, so it will be like so it is giving it is take the data is at list or an array of 1 2 3 4 5. What it is doing is that it is just converting them to tensor. So now you can see this list is a tensor object, and it is very easy to play around with tensor than a list, because tensor has a lot of functionality built on it top of it. So you can just check a lot of things which you cannot do with a normal list. I got a question, what is tensor? So I just explain what is tensor. So if you go back in the lecture, I just explain what is tensor. So it's like it's a way of saying multidimensional numbers. So for one dimensional, you say number. For this, you say array, or for this, you say matrix. But if you tensor is just a term that you can, like, assign for all these numbers and call it as number as 1D tensor, and this array as 1D tensor, and matrix as 2D tensor. It's just term for defining everything. No, it is not a data type. Yeah, you can say this is a data type, but it's just a way to represent numbers. So matrix is so vector is a data type, number is a data type, int is a data type. But you can say that a number is a 1D tensor, and a vector is a 2D tensor. A vector array is a 2D tensor, and a matrix is the vector and array is a 1D tensor, and matrix is a 2D tensor, and this also goes to latter dimension as well. I got another question. After getting ANN model trained and tested, how can we extract the functional relations between input variables and output from a mathematical equation? So I'll discuss that in a bit. So bear with me. And yeah, so we'll just come back to the running our code here. So this is like the tensor we created from the list. Let's just check the size. Like, it's very hard to check size and safe and all these things, like, modifying the tensor, multiplying the tensor when you are working with an array which is Python based. Once you convert it to tensor, it's like a cakewalk. Let's say you have a tensor of this 1 2 3 and 4 5 6, and you want to check the safe of the tensor and safe and size. So the basic functionality is that you like, type dot safe, you'll get the safe. Safe here is 2 cross 3. There are 2 rows and 3 columns, so that's why it's 2 cross 3. The size is the similar thing, 2 cross 3. It's just like, basic way of interacting with an array or multidimensional array, where we call it ND array or n dimensional array. So it is the ND array is a term that related to NumPy, which is another Python library. But since we're using PyTorch, we should be familiarized ourselves with n-dimensional tensor, which is ND tensor. So then coming to accessing the elements. So when you want to access a tensor element, it's pretty straightforward. It is same as any other language. So if you want to access the 0 element of the matrix, you can just type tensor 0, and the name of the tensor is tensor itself. You can name it as A, B, or anything. And if you want to access the second row, it's like saying, give me the second row. So first row is 0, second row is 1, and if you put a column, it will know that give me everything in the second row. So if I run this, you can see it is giving everything in the second row, 4 5 and 6. If I put instead of putting a column, if I just put 0, it will go to second row and first element, which is 4. Instead of 0, if I put column and 3, it will give me everything till 3, I guess. Yeah, it will give me everything. If I just put column and 1, so it will go to the second row and give me the first few element, because I wanted till 1, like it is including 1, so 0 and 1. So it is like this. You can always play around with it and find, like, how this is affecting the element that you're accessing. And also, like, if you want to access the last column, you can put 2 here, or you can put -1 here as well. In Python, the indexing goes both direction. It starts from 0 to n. Also, in the backward direction, it starts from -1 to -n-1. So these are the things for accessing elements, and they are the basic operations. Let's say you have x as this, y as this, and you have to add these two tensor. You can just do x plus y. Make sure that the tensor size should be same for addition. Also for multiplication, you need to make sure that So the way I showed here, the way I showed here, you can multiply x with w. The reason I could multiply because the number of columns is same as number of row here. You know that these two will be cancelled, and the resultant matrix will be 1 cross 4. Here also it is 1 cross 4, and it is 4 cross 1, and it will be resultant will be 1 cross 1, which is again 1. So you need to really care about how the dimensions are there in the tensor and while doing any operation. So this like adding to tensor and it is multiplying to tensor, element-wise multiplication, it is not matrix multiplication. And matrix multiplication is termed as dot product, which you can achieve like dots dot, and if you do dot product between x and y, this will do like this will take x and this will take y transpose and multiply it and add it, which will come around 4, 10, 18, which is and if you add that you'll get 32. 4, 10, 18. Yes, 28 plus 4, 32. And if you want to do matrix multiplication, one way is to do a matmul. So if you Torch has a function called matmul, so it will just multiply this matrix 1, matrix 2, and you'll be done. So if you see in this, if you see here, it is very easy to see that to get this interpret values of this 4 neuron, you need to multiply this matrix, X matrix, with the W matrix to get all these 4 values. So there, you need to like sort of figure out, yeah. There you need to sort of figure out. So there you need to sort of figure out what. Yeah, so this matrix multiplication will be useful there, where you need to multiply the input feature with uh, uh, the weight matrix. So, but I will show you that with this much amount of code, which is very little, you don't need to do this multiplication and everything on your own. It will be done internally, so you don't need to really care about what is going behind the hood. So you just you knew the basics of it, and since you now you will know how to write the code about code for it, you can now will be able to see results without worrying much about how all these things are back propagated and how the rendition is exactly implemented inside the code. So it is a very great tool if you want to move forward with your research or with your project. Just use this tool and you will be able to find result with very fast, without worrying about what is that is going inside and without so of course you will know what is going inside, but without worrying much about the amount of code that you need to write for achieving the same thing. I got a question that I can run the code. So Yosita, so run this first block. So there is a first block saying import torch. So you have to run that first, then run the subsequent blocks. Then only you can get the results. Okay, so yeah, thank you. So now we'll do the classification with ANN. We don't have much time left. I'll try to complete this as soon as possible. So now we have like classification with. So now we'll study about how to write the code corresponding to everything that I discussed today in the lecture. Let's say, so you want to do this, right? Your voice is not audible. Yeah. So let's say you want to do this classification. So for this, you need a couple of more libraries. So yesterday you saw that yesterday you learned about this pandas. We imported pandas, and today we imported torch earlier. Apart from torch, we need to import two more internal libraries of internal functionality of torch. One is NN and one is Optim. So you'll know in a short while how these two will be used. And apart from that, we need these two functions from this library that is called sklearn. Sklearn is also a famous library, which full form is scikit-learn, and it is all installed in Colab, so we don't need to worry about installation and stuff. So let's just import this library by running this, and you need to again go to this file icon, and you again need to upload your titanic.csv file into it to work with it. So please upload the titanic.csv file and run the second block, which says loading saved. Oh, sorry, it should be loading dataset. Loading the dataset. Yeah, loading the dataset. You load that. So I'll wait for everyone to load the dataset, and I think it should be easy now because you did yesterday. So yeah, so I hope everyone loaded dataset. Then we prepare the dataset. We sort of started. We sort of started uh, uh, so I didn't do much preparation here, which maybe that's why the accuracy won't be that much great. But we did a lot of pre-processing yesterday. If you could recall, we went and we sort of found out which columns have missing values. If it is more, we just discarded it. If it is less, we sort of tried imputing it, or you can say filling it, or we sort of removed the unuseful columns. But here we just we're just sticking to this sticking to this uh, very simple preprocessing where we just drop all the NA columns, and we sort of took these simple 6 columns with us, and will not include the sex here. So I'll show you the difference while I include the sex column. So let's say we took this 5 column and we assume that a person is dead or not will highly depend upon these five columns, like what is the class of ticket he booked, or the age of the person, or the part, the point he took the ship, and the fare he paid for the ship. But if you if you think about it, so these are the just some features which I think is responsible uh, for that person to survive. If it is very aged, he might not have survived. If it is a young person, he might have survived. So taking that thing into account, I'm assuming that uh, these are the few things I should take as my features, and survived or not survived is the label that I'm trying to predict. So I named my features as X, and I named my all the labels as Y, and I run this block. So we did some normalizing stuff here. So I'll just briefly talk about what normalizing means in the context of machine learning. So when you have data, so you have a A's column that goes from 0 to, let's say, 100, and you have this pair column that goes from, let's say, 100 to 1000, and let's say you have there's the class column that is either first class or second class or third class. So if you look at these numbers, so these are your X, and you will be predicting your W's. So if you look at these numbers, it is very diverse. So this value will always be between 0 to 100, and this value will be 0 to 1000. Some feature might be there which is not in this case, but it can come in 10 to the power 5 to 10 to the power 10. So it is very difficult to work with numbers when the range is very varying. So what we do is that we do standardization and normalization. By doing standardization and normalization, what we do is that we scaled everything to the value of 0 to 1. So all the smaller values will go close to 0, or the larger values will go close to 1. In that way, all your value will be like distributed across this line. So this is normalizing, like so normalizing means like it will lie between -1 to 1. But if you like if you do standardization or scaling, it will always lie between 0 to 1. So if the value is lies lying between 0 to 1, it is very easy to work with, and also your values will not explode into much large numbers, which the programming language might not handle sometimes. So this is the reason behind standardizing and normalizing. And here it is like normalizing the feature using standard scalar. So we'll run that, and then comes a interesting part, which is called train test split. So I imported, if you see, this train test split from scikit-learn, so and imported this standard scalar as well. So we used standard scalar first. Now we will be using the train test split. So train test split takes this x and y and take the test size and takes the random state. Random state is just a initial variable for using a random variable, but I'll just discuss about the train test split. Let's say you have a data set this big, and you have your features and labels for it. You want to train a machine learning algorithm with the data set, but at some point you'll be like requiring to test this your trained model. It's not like that you just train and you just assume the detail work fine. So what you need to do is that you need to find a chunk and use that for training, and it should be bigger chunk, and use the rest as test. This is called train test splitting, where you split the data set into two parts: training and testing. So there is a notion of validation test as well, but as of now, I will not talk about validation set. I will just talk about train and test. So from this, you can you can see that training and testing are two data set, and when you train a model using train set, it will have no knowledge of test set. So when you test your model with test set, it will give prediction, and by that prediction, using that prediction, you can easily sort of assume that how good your model is or how bad your model has trained. So from that you can only say that will this model be performing better in the real world or not. That is all about train test split. I don't think that is a big thing to discuss. So I run that cell. Then coming to defining the network. So let's just go back to our yeah. So let's just go back to our discussion in the board. So we are predicting Titanic, and we have 4 feature in hand, I guess. Let me see. We have 5 feature in hand. So we want 5 input layer. 1, 2, 3, 4, 5 is called 5 input layer. We want some hidden layer as well. Let's say we want 8 hidden layer. Not 8. Let's say we need 4 hidden layer. So this number of hidden layer, number of hidden dimension is all very flexible. You can choose, and this is my output layer. Since I need to only predict if it is alive or dead, if it is Above 0.5, I can say alive. Below, I can say dead. And I connect everything to everything. That is called fully connected neural network, where everything is connected to everything. And there is something called, so also this is called sequential network, where one output of one layer goes to the other layer. So this all are connected, and this is also connected. Now I'll so this is a way to learn this, uh, underlying function. So the input variable is 5, hidden is 4, and output is like 1, and we need to code this up. For coding, so this is the exact format that you need to follow. So you want to ML model, you name it in the class name, and you use this as a child class of this nn.module. And here, this is the initialization, this is the constructor where you pass the input dimension, hidden dimension, output dimension. So you just need to keep everything same. Just so this is FC1 and change here. So if you just change here, the architecture will be changed. So I'll now show you how exactly you are designing that's something that we do here. So here we did a linear layer where the input dimension is 5 and output dimension is 4. Here, if you see FC1, the fully connected one, is a linear layer, which is between input dimension and hidden dimension. So value of input dimension, if you see here is taken from the X, which is 5, and value of hidden dimension is 8 here. But for our simplicity, we take 4, it is 8. So which is again a hyperparameter you can change. So this is the layer number 1. This is corresponding, this line corresponding to your first layer. Then you put a ReLU. So ReLU means, so as I said, you need like as I said, you need a better sort of non-linearity to do all these things. So that's why we put ReLU in top of linear, and again there is a linear layer between these two, this layer and this layer, 4 to 1. So here is again a linear layer between the hidden layer and output layer. And at last, since I said it is a binary classification problem, dead or alive, the function is sigmoid. The function activation function we are using is sigmoid. It's the difference. Here we are using ReLU in the intermediate layer, but sigmoid at the end layer. So we define the forward function. So forward function is defined for the forward pass. How you want your X to travel. So here, as you see, it is defined that X will go to the fully connected layer 1. You'll get the output. That output will be passed through ReLU. You'll get the next output. That output will be passed through again the second layer, the 4 and 1. You'll get output, and the output will be passed through the sigmoid. So all these things you defined here, and how the input will be passed through all these things will be defined here in the forward process. So if you want to make some changes, you can do. I'll show you how you can make some changes and see difference in the performance. So this is all done. You have now defined the model. Then defining the loss function and optimizer. So loss and optimize, not optimizer, it's optimize. It should be not optimizer, it should be optimizer. Optimizer. Yeah. So so here you decide the input size, hidden size, and output size. Here you define the model. Here you define the loss. So I mentioned that NN is a internal thing that we are importing. From NN, you can decide the loss actually. And for binary classification, you need binary cross entropy loss. So I mentioned here about 3-4 losses that we will discuss. Mean square error is for regression, where you just subtract between two entities by taking square difference. this binary cross entropy is for multi-class classification. Sorry, binary classification. Cross entropy and negative log likelihood is for multi-class classification. So you just need to remember that. So I'll give you the detail later how these laws are capturing all these things. But for now, since it is a binary classification problem, we'll use binary BCE laws or binary cross entropy laws. And the way I said to update the weights. So to update the weights, you need optimizer. So optimizer here you are using Adam. So the one I showed is called stochastic gradient descent or SGD. You can use SGD as well, and check the performance. But we're using Adam here, and to update the weights in using the Adam function, you need to pass the weights as well, weights or the parameters. So you can just access the parameters of the model by model.parameters, and LR or the learning rate is the step size or the alpha that you need to decide. So here I have decided as 0.001. So these are all the hyperparameters that you can choose. So if you are asking which loss function to use, then there is a definite rule. But if you want to use which optimizer to use, which learning rate to use, what is the hidden size here, what should be the output size here, then I cannot answer that because it is very specific to task, and you have to hit and try with different combination to find the optimal one. So let's just run that. And this is the code for training the neural network. So exactly how this is same with the similar to the 4 steps that I mentioned. So the first initialize the randomly. So that is done internally. When you define the model, it will be done. So you don't need to worry about that. Then step number 2, forward pass. Forward pass is just this line. You take the model, you pass the train X train to it. You get the outputs. That's the forward pass. That's it. So when you call this, when you pass the X train to the model, it will evaluate this forward function. So it will, all these things will evaluate. You don't need to worry about how to multiplying X with W, getting the output, and then getting putting activation function on top of that. You don't need to worry about that. You just need to pass the model X train, you'll get the output. Once you have the output, the second step is that this is I would say step 2. Step 1 is done. Step 2, and once you have the output, you have to do the step 3, which is calculating the loss. You already defined the loss here and named as criterion, which is the binary cross entropy plus. What you need to do is just call that loss with output and the actual y to get the loss. You found the loss. So the way I calculated the loss earlier by subtracting the y hat from y is a naive way of doing it. Actual way of doing it varies from task to task. For this, since this is the binary classification task, the loss we are using is BCE. And then we have to do this backward propagation, where we propagate the gradients towards all the weights that is there. So these 3 things you need to write. So first, this optimizer dot zero grad will zero out all the previous gradient that it have. Then loss dot backward will just do the backward propagation. It is very complex problem, so you're just getting it in one line. Then optimizer dot step will update the weights. So this step, this line W equal to W volt minus this gradient of loss with respect to W into alpha will be executed with this line optimizer dot step. You're just taking a step. You're taking a step in the opposite direction of the gradient, and in this way you need to perform this 1,000 times. After 1,000 iteration, you can hope that your loss will be converged. And I have again put a print statement here. If the epoch is a multiple of 100, let's just print the loss, and so that we can see if the loss is increasing or decreasing. I'll just run it now. Yeah. You can see the epoch ran till 1,000, and the loss decreased from 0.65 to 0.55. Let me increase the iteration from 1000 to 10,000 now and see. The loss now decreased till 3.7. 3.7. So by increasing the iteration, I can see that the loss is also decreasing. Then this is the piece of code to evaluate the model. So we had test set ready, separately. We can now evaluate the model with the test set. And if we evaluate that, we can see that we're getting 64% accuracy on the test set, on the set which the model hasn't seen yet, and getting 64%, which is good, but not so good. So to do that, so to improve that, what we can do, we can keep this to 1000 and see what is the accuracy that we are getting. Yeah, the accuracy is same, 64, no change. So we don't need to go for 1000 then. So let's just not tweak around. Let's just change the learning rate a bit. Let's just increase the learning rate from 0.001 to 0.01 and see if it is affecting the training or not. No, not it is the same 0. Let me 0.05. The accuracy is not increasing, it is still 64. Let me put the this to 0.001 and add a additional column. So we can increase the neuron in the hidden layer as well. From 8 to I can increase to 16. Let me see if it is making any changes. Yeah, it increased a bit. Now it is 0.67, which is 67%. I don't think it is visible. It should be it will be visible to you because it is very small. The text is very small in the output domain. But if you run from your side, you can definitely see that. So let's just keep the hidden size as 16 since it has increased it. Let's just make some changes in the data. And what so it's always the features that you consider while making a prediction. So since you are predicting if the patient is dead or alive, so if you let's say think about sex, you can say that you can assume that it is very clear to see that gender of a person plays a vital role in saying if the person is alive or dead. Because if you recall, women and children were allowed to go out of the Titanic first. That's why it is highly likely that if he sees a woman and she will be alive. So let's just include the column sex as well in our analysis. And as you know, sex is a text based column. So we need to find the one-hot encoding of that. We did that yesterday. So I'll just run this and I'll run the other blocks as well to see if there is an improvement in the accuracy. Let me see. Yeah. So you can now see that the accuracy jumped from 64% to 78%. Let me increase the number of epochs now. Yeah, the accuracy dropped now. So you shouldn't increase the epochs actually. You can decrease the epochs and see. Yeah, decreasing also is not working. Let's just keep it 1000. Yeah, the performance dropped again. I'm not sure why. I think I made some mistake. But the thing is that the thing I wanted to clarify is that if you play around with the features, if you play around with the learning rate that which is the model is learning, if you play around with the the epochs and all, you'll be getting much better accuracy, such as 78 and 38 or 78.38 for a task. So I would request everyone, for everyone of you to like sort of uh, do this in home tonight or tomorrow, play around with it and find what are the other features that you think is crucial. So we have all the features that is there: name, age, ticket, fare, cabin, embarked, sex, and all. So just find, so apply all those data transformation that I taught last time, and apply all those data sort of pre-processing techniques, and see if you can go beyond 78%. If you are if you can achieve beyond 78% by doing anything, by adding a new layer, or by changing the activation function, then do let me know tomorrow. We'll so that in the lecture what change would improve the test accuracy the system. So for now, for today, I guess we will stop here. So we'll see you guys tomorrow, everyone. And I will share this notebook, and the recorded session will be put in the YouTube by ma'am. And yeah, thank you, everyone. Okay, I'll share the PPT. I'll share the entire folder with PPT recordings and uh, notes by tomorrow. Give me time till tomorrow. Ma'am, I guess we need to. If you want, you can make an announcement. I guess we can stop the meeting now, ma'am. And so Yeshua is asking for quiz link. So I don't have quiz link. Ma'am will coordinate the quiz with you guys. So I think I'll end the meeting now. And thank you everyone for joining. Thank you once again. If you want to connect with me, I'll share my